look, the further back we're looking in time. And so we're designing the James Webb Space Telescope to see past the point where Hubble could see, and to see the very first stars and galaxies to light up in the Big Bang. To see those very, very distant galaxies, the light from those galaxies has been redshifted. The expansion of the universe sort of stretches space-time. The light from the galaxies gets stretched as well. And so longer wavelengths of light are redder. And so at some point in the very distant past, the light from those galaxies has been shifted, redshifted, all the way out of the visible spectrum to the infrared part of the spectrum. So having an infrared telescope in space is one of the things that's going to allow us to see those very first galaxies.
essential to study our own solar system because that's sort of what we're comparing all the other planets around other stars to. We had to make sure this highly sensitive, huge telescope that's designed to detect the first stars and galaxies across the universe could actually look at the biggest and brightest things in the solar system that are also moving at very fast rates of motion. So it was my role to help establish moving target tracking for all these small bodies in the solar system. My science goal for JWST involves the entire solar system. So observing everything from near-Earth objects to giant planets and their satellites, icy worlds, Europa and Enceladus, things that have plumes and we suspect oceans underneath their surface, to the farthest reaches of the solar system, so things like trans-Neptunian objects or Kuiper belt objects, even Pluto and its satellites.
Webb will explore every phase of cosmic history, from within our own solar system to the most distant, observable galaxies in the early universe, and everything in between. Webb will reveal new and unexpected discoveries and help humanity understand the origins of the universe and our place in it.
Whatever happened on Earth, it's not likely to be rare or unique, because carbon chemistry, on which life is based, is the most fertile kind of chemistry there is. Carbon is abundant across the universe. So if there's life somewhere else, it's probably based on carbon. It's a fascinating bias, but it's not an unjustified bias. And the universe has been around 14 billion years, plenty of time to evolve all manner of creatures out there, particularly microorganisms. We have no reason to not think of microorganisms as aliens. They don't have to have built a ship. There's just alien life on another planet.
We learned that asteroid impact, when they hit, can cast rocks in the surrounding areas into space with escape velocity, so they never come back to the planet from which it was launched. If Mars was wet and thermal before Earth was, as all evidence suggests, and if Mars had life before Earth had life, it is possible for there to have been bacterial stowaways in the nooks and crannies of the rocks that were cast into space. There's some hardy bacteria that we already know exist on Earth. Survives extreme temperatures, pressures, freeze dry, reconstitute, radiation. The hostile environment of space will be nothing to some of these bacteria. It may be that life on Earth is seeded by bacterial stowaways on rocks cast free from Mars. This is a plausible scenario that's called panspermia, transference of life from one planet to the next.
Life on Earth is hydrogen, oxygen, carbon. This stuff is everywhere in the cosmos. It's a huge universe. We're made of very common ingredients. If you want to believe that life on Earth is the only life in the universe, in a way that's kind of inexcusably egocentric. There's no accounting for that attitude, unless you have some sort of philosophy that requires it of you, but it's not based in data or evidence. So I want to look for life. And life on Earth, if we use that as a starter kit, thrives in liquid water. So if you want to find life, let's look for liquid water out there. And so we know Mars has all this evidence of once having had liquid water. We think it's submerged and now in a permafrost. And maybe if those pressures are high enough, some of it might have been liquefied, creating aquifers. Recently we found methane emerging from one of the cliff faces of Mars. Methane. You can make it without biology, but biology kind of does it for free with sort of anaerobic microbes, the kind you find deep in the digestive tract of farm animals. One of the moons of Jupiter, Europa, is kept warm. It's way outside of the green zone, that zone where this Goldilocks zone, where the temperature is just right. Because if you're too close to the sun and you have liquid water, you evaporate. Too far away, you freeze. So there's a zone where it's just right, where it's liquid. This Europa is well outside of this green zone, this old Goldilocks zone, yet there's an ocean of liquid water, been liquid for a billion years. Turns out the gravitational stress of Jupiter on that moon, combined with stresses triggered by other moons, is pumping energy into that core. And when you do so, where does the energy go? It melts the ice. There is this zone around any star where if you are too close, then liquid water would evaporate. If you're too far away, then your liquid water would freeze. And water being so crucial to our understanding of life as we know it, if you're going to look for a planet in search of life like us, you would look for planets inhabitable. And I think of it as the Goldilocks zone. And if a star gets hotter, it'll still have a Goldilocks zone, it'll just be different. On the frontier of scientific research, ideas are contested, and most ideas turn out to be wrong. And the successful idea is not the one that's argued most strenuously. Either of those, it has to do with evidence. Which idea is supported by evidence? When you have repeated experiments verifying an idea, we have a new objective truth that has emerged in those sciences. And what I'm telling you is that the Big Bang theory, then you get to the origin of the universe. The tenets of the Big Bang, that the universe started out small, hot, dense, where matter and energy were a primordial soup, where the forces of nature had merged. All of that is thoroughly supported by observations of this universe. Thoroughly supported. There's some things that, well, did this really cause that? Or might it be something that we don't know about yet? And who ordered up the dark matter? We don't know where that came from. And where's this expansion? We don't know where that came from. But we can describe it, and we can measure it. Here's the point. If tomorrow you have a new idea about how the universe works, it's going to enclose everything we've been talking about up to that moment that has been experimentally and observationally verified. You can enclose it in something deeper. Okay, you can say, oh, wait, I have an idea. Our universe is just one in a multiverse. Fine, okay? But our universe would have started with a Big Bang, okay? And our universe would have expanded from a dense, hot state, and it's been cooling ever since. That's observed, and that's real, and that's not going away. And if there's some little thing in the early universe, and some new idea is emerging over another idea, Big Bang is not in trouble. It is a whole thing that could conceivably fit in a deeper, bigger idea. But it's not going to be swapped out tomorrow. We're not going to find out tomorrow. The early universe was cold instead of hot. That's not going to happen. That's not how science works.
So if you're going to come up with something new, you're not coming up with something that will change the old.
When we think of Einsteinian physics, so it's relativity, which completely usurps Newtonian gravity and Newtonian motion. Einstein comes along with a special theory of relativity, and then his general theory of relativity, and what we find is that at high gravity, like near the sun, and at high gravity and high speeds, Newton's laws completely fail. You cannot use them at all. So Einstein basically enclosed Newton's ideas as a special low-speed, low-gravity case of a much larger, deeper understanding of the universe. There's no way to understand black holes with, or even the Big Bang itself, with just Newtonian physics. New physics does not undo experimentally verified physics. And so the Big Bang is just fine. You want to do something else with it? Take it body and soul and stick it in some other theory you have. But you can't undo what the experiments and observations have shown. And that is an explainer for you. That's an explainer.
So, what was before the Big Bang?
However, another answer is that the very question may not make as much sense as the words seem to suggest. We know how to parse that sentence. We know what it means to talk about the moment before the Big Bang because we fully understand the meaning of that kind of sentence. But it could be that when it comes to the Big Bang, the sentence actually doesn't mean anything. It could be that the Big Bang was the place where time itself started. Talk about a billion years ago or 10 billion years ago, but if you go to 13.8 billion years ago, the Big Bang, that may be where time started. And you can't go further back in time than the very origin of time itself.
There's nothing wrong before, we just don't have any data. I don't mind going into negative time. I have no problem with that. I don't mind resetting where the 0 point is. Time is just, where you put the 0 is arbitrary, as it continues to be this day with calendars. And so the starting point is just where you want to put it. And so right now, a pretty good starting point is the Big Bang. We don't know how to put it earlier than that. But if the day comes where a whole new kind of understanding of the universe reveals to us before that, I don't have any problem pushing the 0 point back or just counting into negative years.
The idea that I think most physicists or cosmologists buy into at the moment is that gravity can have two manifestations. The usual form of gravity is the attractive version. You drop something toward the Earth and it moves downward because the Earth and the object pull on each other. That's the ordinary gravity that we experience every day of our lives. But Einstein's equations actually allow gravity to also be repulsive. It can push outward as opposed to just pulling inward. And this is something that we have never experienced because the gravity created by a rocky object like the Earth is always the attractive variety. The gravity created by the sun, again, a compact object, is always the attractive variety. But Einstein's math shows that if you don't have a rocky object that's isolated in space, but rather energy that is uniformly spread through a region of space, that kind of entity yields repulsive gravity. If the very early universe, if it was filled with a uniform bath of this energy, we call it the inflaton field, the name doesn't matter, but if it was filled with that energy, it would have been subject to repulsive gravity. What does repulsive gravity do? Pushes everything apart, causes everything to rush outward. So the bang of the Big Bang may have been a spark of repulsive gravity operating with a tiny region of space that pushed everything apart. It could be that the Big Bang was an interesting event, but not the first event in the totality of reality. It could have been the first event that sparked the expansion of our part of space. But it could be that there's a grander realm of space within which we sit as a small part, and that grander realm may have been here for a far longer period of time. It may have experienced its own Big Bangs, maybe a collection of Big Bangs that may extend infinitely far into the past. So it could be that the answer to the question of what happened before the Big Bang is a lot of other Big Bangs or a lot of other quantum events that were taking place in a larger landscape of reality than we have direct access to.